Hello, we're going to finish up on our volcano notes today and taking a look at this picture. And obviously, this is available in the notes, so go ahead and look there if you need to enlarge the picture more. But what are the components or parts of a volcano? And move this a little bit. There we go. You obviously have your magma chamber where we're getting our molten material. And the interesting thing about it is it can go out into multiple areas. This is an intrusion. It's technically called a dike, and it cuts across the different layers. So obviously it's not going past there and it's not making to the surface, but this one is really close to the surface. This is your vent, the main vent, as a matter of fact, and this can be sometimes called a sine vent or a secondary. And you can actually get some magma coming out the side. It doesn't just have to come out of the top. And obviously, we've got our gas and our ash and our lava flow out. Remember, down here, it's called magma. And once it erupts from the volcano, it's called lava. So, what is basically a volcano? It's really a weak spot in the crust where magma comes to the surface and erupts as lava. And it's formed down in the mantle where it's heated. So it's all that silica and the other melted materials down there that come to the surface. And if it's at a subduction zone, remember, it can be really sticky because it's got all that organic matter and water, stuck in it. So lava reaching the surface and magma's under the surface. There's 3 types of main volcanoes that we started talking about in the last set of notes. And this is just a quick review. The shield volcano is really flat. It's right here. It's like Mount Fuji. And cinder cone volcanoes are really sticky lava, and they build up really high, where the shield volcanoes are really runny lava, and they just spread out far. So you get the low dome, where a cinder cone is really tall. But a composite volcano, sometimes called a stratocone volcano, is alternating layers of that sticky stuff and the flowy stuff. And you really get taller volcano than the shield, but a wider volcano than the cinder cone. And it's literally that combination of the two. This is a map of where you're going to find the volcanoes. And interestingly enough, doesn't it seem to have a lot of similarities to where our earthquakes happen at our plate boundaries? And that's because these are subduction zone volcanoes. You have this ocean Pacific plate being subducted under Asia and under the Americas here and under Australian plate there. And then, of course, here we've got the mid-Atlantic ridge, and that's just kind of constantly going. In here is just a really quick, watching some eruptions of magma. And you can go back and watch that if you want. So again, let's take a look. A shield volcano has its reservoir here, but has low viscosity. It's gas poor magma, where our crater on our stratocone, which is the combination, has a higher viscosity and it's gas rich. So you get a slightly taller than the shield, but it's wider than the cinder cone. Obviously, you'll have some questions. This is actually on a brief quiz at the end of the day to just go back and work on that, because I want you to have some practice identifying different types, and you've got like 20 attempts at it. So don't freak out. There's only 6 possible choices for each one. So non-explosive eruptions, you're really talking Hawaii in this case. It's they don't like blow their tops, as it were, but they can erupt in your backyard if you happen to live close to where there's vents. And that was happening a couple of years ago, where all of a sudden there would be fissures opening up and lava coming out. Well, maybe we're not going to watch that. Let me try that again. Guess not. Well, it's in the notes if you want to go take a look. Okay, so Hawaiians have so many different terms for lava, but the 2 I'm going to make sure you understand are a'a and pahoihoi. And pahoihoi is this really viscous stuff that it just kind of, as it cools, it bends and twists, and it wouldn't be that bad to walk on. It's not really rough, and so it's pahoihoi. But a'a is really This is sticky stuff. This does not want to move very much. It's really rough. That's like, I don't want to walk on it, and hence the name, lava. Pillow lava is literally lava that's simply erupting and cooling underground. And as it comes out, it forms these pillow shapes because the water cools the lava quite quickly. There we go. At least this one's working. So we've got our molten material.
Rivers of liquid rock plunge over the cliffs and into the water below. This is the front line in a battle between the elements.
You can get pipes going out.
But inch by inch, the island grows.
And again, here we've got our pillow lava. This is what I want you to really look at because it's constantly erupting, but the water is constantly cooling it. Again, all of these you can go back and watch as you have time.
The study of the atmosphere of the ocean at the University of Washington. I was the chief scientist on this expedition, so I led the cruise and the trip to the West Nile eruption. The video that you'll be looking at is large magma bubbles are about 3 feet across, and the bubbles are molten rock that are expanded under the gas pressure of magmatic gas. And the magmatic gas, we presume, is mostly water, and when the water is under the magma, that magmatic temperature is thousands of degrees, and when it suddenly cools by coming in contact with seawater, the bubble bursts. What excites me the most about this volcanic eruption is that that on planet Earth, this is a process happening all the time, and yet we have never seen it happening quite this way. The ocean floors are formed almost exclusively by volcanic activity. And strangely enough, we really have never seen molten lava flowing on the seafloor from a submarine volcano. We have seen in other eruptions much shallower in the ocean, but in this case, we're actually seeing molten lava flowing on the seafloor. We're seeing these magma bubbles. We're seeing these explosive events. We're seeing the seafloor open up and pour out magma. And we're seeing these pillow lavas, probably one of the most common forms of rock on Earth.
Remember, our ocean floors are really basaltic lava, so that's what they're made from, exploding or erupting volcanoes. Exploding volcanoes they have a lot of pressure buildup, and they've got a lot of stuff that makes them want to blow. And then all of a sudden, when they have enough release of pressure and enough pressure is built up inside, you get an explosion.
This is it, was the excited call on the radio from David A. Johnston.
And this is Mount St. Helens.
Within minutes, the colossal eruption had caused hundreds of millions of dollars in damage, and 57 lives were lost, including Dave Johnston.
He was
For
a
2 months
volcanologist.
prior to that eruption, scientists with the U.S. Geological Survey and the University of Washington's Pacific Northwest Seismographic Network had been closely monitoring the volcano.
All the deformation on the mountain was local to the mountain, and even more local than that was on the north side of the mountain. In the nearly 2-month period before May 18, what was essentially happening at Mount St. Helens was that magma or molten material was moving up from some deep reservoir beneath the mountain up into the volcano itself. And it began to grow or form what we call a dome or a cryptodome inside the volcano. And that inflating body of magma or molten material actually broke the north side of the volcano and began to cause the north side of the volcano to expand out toward the north.
We were measuring the rate of northward movement of the balls at about 6 feet a day, and
that's a lot.
That wasn't so good.
On the morning of May 18, I was driving up Interstate 5, headed up to the north side of Mount St. Helens with some parts and some batteries for our time-lapse cameras. And as I glanced over at Mount St. Helens, it was a beautiful blue sky day, and the mountain was sitting out there, and suddenly I saw this mushroom cloud go up above the volcano and climb rapidly up into the stratosphere.
And I was down in the room where the seismographs were at 8:32 in the morning, and I heard a sound, and I just looked over my shoulder, probably just a split second after the big earthquake had started. and saw that this was something very large, larger than we'd seen before. Watched it for a few seconds just to confirm that. And then I ran upstairs to the next floor up to the radio desk of the Forest Service and called Dave. And we couldn't get through. There was no answer.
So I guess I had the realization right away that this was some kind of a tragedy. And on the one hand, it was this huge, exciting, and interesting magmatic eruption, and on the other hand, I was pretty certain that something terrible had happened to Dave. So it was a strange day for me.
And we were off the ground probably at 9:05 or something like that. I mean, it was really, really rapid, and got up to the point where we could really see the mountain well. I suppose between 9:20 and 9:25, like that. There was this terrific, very vigorous vertical eruption column. There was the stem of the mushroom where the toadstool had been blossomed out at greater height. And for most of the morning, we saw this tremendous ash cloud roiling out toward the northwest. And I can only assume that was coming off of the big pyroclastic flows that were going off in that direction that later built upon the plain. It was a very eventful morning, but it was.
So if you live in the Pacific Northwest, they don't really have tornado practice drills like we do, but they do have pyroclastic flow evacuation drills. And that's not something we really deal with here.
Sobering, because I remember thinking up in the airplane that Dave just couldn't have survived this, especially when we got around to the west side and saw all this ash headed in his direction.
On the morning of May 18, what actually happened? The landslide basically uncorked this pressurized body of magma and allowed it to explode or expand out towards the north very rapidly. This is what we call the lateral blast. It was a horizontally directed explosion of incredible magnitude. It caused this expanding cloud of ash, rocks, and gases to move out across the countryside to the north at speeds of several hundred miles an hour. The directed blast was really the most destructive event that occurred on the morning of May 18. It completely destroyed an area of 230 square miles in a matter of somewhere between 5 and 9 minutes. It essentially killed every living thing within an area of 230 square miles. And it destroyed hundreds of acres of virgin forest. And it's an incredibly spectacular event.
We put on news stations and we quickly started to remonitor the volcano again because we had no idea what was going to happen.
Before the dust had literally settled in the summer of 1980, there were USGS scientists swarming all over the area out in the blast zone, studying the pyroclastic flows, studying the debris avalanche deposit, studying the directed blast deposit.
We thought it's likely that there would be more eruptions during the summer, and indeed that took place.
And suddenly this immense black eruption cloud came pouring up out of the white layer that the cloud tops. And I couldn't believe my eyes. I mean, I thought this is the most incredible thing I've ever seen in my life.
We learned a lot about how you interact with civil defense, with the public, with the press. And that was transferred by the press to the world. And as a result, I think volcanology took a quantum leap in science as well as applicability to society's needs.
The subsequent eruptions were actually, most of them were forecast fairly accurately by the USGS team of scientists. So when it looked like another explosion was about to take place, our helicopter crews would pick us up and we'd move out to the outskirts of the blast zone. We'd watch and photograph the next eruption. As soon as the eruption stopped, we'd race out there and study the deposits while they were still hot, while they were just after they'd settled onto the ground. So it turned out that the 6 years that Mount St. Helens was erupting in the early 1980s was an unprecedented opportunity for USGS scientists to study hot, fresh, young, and exciting deposits from explosive volcanism. We learned incredibly new and important bits of information about how volcanoes like Mount St. Helens work, what kinds of deposits are produced during these explosive eruptions, and how to anticipate and mitigate the consequences of explosive eruption.
Okay, so really it's the composition of the magma that determines how explosive it is or is not. So high water content, more likely to be explosive. So subduction zones. High silica content, more likely to be explosive. Silica that has a thick, stiff consistency, it flows slowly, it wants to get bogged down and kind of bunched up, and then all of a sudden the pressure builds up enough and it just explodes out. And it tends to harden on the volcano's vent, therefore making it steeper and taller. So pyroclastic material that we talked about in there is those fragments of rock and ash and gases that literally flow down the sides of the volcano. And it can have, there goes my mouse. You can actually have something called volcanic bombs coming out, and they kind of look like the shape of a football, or in this case, it kind of looks like a nut. But that is lava that got thrown out, ejected out, and it kind of spirals through the air, and it can actually become like football shaped. These are called volcanic bombs. So this, if I remember correctly, this is an Icelandic volcano. This is not very viscous. This is sticky stuff, but it does throw out bombs. In fact, at one point they're going to actually have to move the camera back because it starts shooting out right at them. And again, if you want to see more of the eruption, you can go back and look at it. So volcanic blocks, kind of like volcanic bombs, except this time they're just a lot bigger. And it's just hardened lava, and they form big blocks of rock. Ash is really fine pulverized volcanic material, and it can flow out. The interesting thing is when it erupts, it stays in the atmosphere. And so like right after Mount St. Helens or after other eruptions that have a lot of volcanic ash, that grit is like sandpaper in the sky for airplanes, and their windshields have to get replaced more often because they literally just get scratched from the volcanic ash going through the air. This is an eruption that happened a couple of years ago.
Mount Ataki, the recent eruption, 11:53 local time. This is the location of the volcano in central Japan. You can actually see the crater on Google Earth. This is what erupted just a few hours ago. Of course, some really incredible footage being caught by some of the hikers that are currently stranded on the mountain. Take a look at this. You can see the ash cloud.
That's a
just
flow of gas and
into
ashes.
the atmosphere. Very, very scary situation to obviously be on the ground to impact or feel the impacts of this. Obviously, some tremors being created from this particular volcano as well. The local police and the Nagano Fire Department has received several reports of injuries, and the Japan Meteorological Agency is forecasting further eruptions as well. Take a look at the footage now, Zane and John, because the ash cloud actually reaches the climbers. Listen. This is really compelling video, if you ask me. This is really just fresh off of YouTube, and of course, with Japan actually.
So here's the moral of the story: don't hike on an active volcano. Volcanic lapilli is basically size classified for tephra or volcanic ash. So you're really kind of looking at different sizes when you're looking at this, from really fine up into, a pretty good size pebble. Lava fountains are just what this sounds like. It's a fountain of lava coming out. Sometimes it's a tube lava and it goes into the ocean. That's really cool. Or it can be a straight up pillar, or in this case, it's ejecting laterally. This one has one so tall it's the height of 2 Empire State Buildings. And this is beautiful. It's like this huge dome of lava. They're called lava fountains. Again, I'm not going to show all this, but I'm just going to show you what it is if you want to go back and look at it. This is Iceland again, and it's some of their eruptions. And this is that black lava. And it's just a very sticky, pushing out. You can also get more fountain-like things. It just depends on the part of the eruption that's happening and how The consistency of silica and water is present in that magma before it erupts into lava. So you can get all kinds of eruptions happening in Iceland. This is 9 minutes of eruption. So again, I'm not going to show you the whole thing. I just wanted you to see different parts though. So sometimes this is a flood basalt area. This is that rifting area. So this is not going to be the big cinder cone mountain or the shield volcano. This is the spreading. This is making Iceland bigger. If you want to look at this, this is the top 10 deadliest recorded volcanoes that have gone through, and they go throughout the different time periods. So in this case, I'm not going to go through all of it, but number 10 happened in 1600. And you can go all the way down to number 1. Fallout, that is the hot ash, can flow fast, very, very fast. It can knock down buildings. It can dam up rivers, causing flood and then drought below. It can kill livestock and anything living around it. It can change the climate. In the 1800s, I believe it was, we had a year without the summer because basically there had been this huge, I'm going to say 1880s, eruption that had occurred. And with it, so much ash had gone into the atmosphere, it blocked out sunlight, and it can actually drop global temperatures. Craters and calderas and lava plateaus. So a crater is basically the opening at the top of the volcano. That can be active. It can also harden and fill in with water, so you can get a crater lake. It can blow its top off, and you have little ridges around it. A caldera is a much larger depression, forms when magma chamber empties and the roof collapses. So this whole area had a magma chamber that receded, and you can see here, magma fills, bulges this up, and then the magma drains out somewhere else, causing it to collapse, and you get this big caldera, and quite often they fill in with water. This is, I will watch this, is 23 seconds. This is a draining of a chamber, and then it floods, and then it erupts, and then it hardens a new layer on top, and then it collapses in on itself. And then you've got the hot molten until it hardens up again. So a lava plateau is literally a plateau. It forms when lava erupts from long cracks or fissures and spreads out evenly. It doesn't form a mountain, it forms a plateau. Obviously, we've got some questions here, and they will be embedded into the video. Thank you for watching. As always, get a hold of me if you need help or have questions.